Hi viewers, welcome to LMS Solution. Today we are going to see about field oriented control of PMSM with the PA controller and space vector modulation technique. So this is a simulating model we created for a FOC control of PMSM with the PA and phase vector modulation. The FOC control, right? Field oriented control of PMSM, right? So here we are going to decouple torque and flux control. Okay, so you have to decouple the torque and flux, and then it's going to be control like a DC motor. Okay, so when you control like a DC motor, so you can easily control that means easily control the PMSM motor with the efficient way. So that's why we go with this field oriented control. So also it is known as vector control. Okay. So in FOC control, right? So we need to convert that ABC stationary ABC frame into rotating DQ frame. Okay, so that DQ frame aligned with the rotor magnetic field. So this is the first step in the FOC, right? So just you have to measure the current and voltage, right? So that should be converted into DQ frame, and then the DQ frame should be operated along with the rotating magnetic field. And then what are the key component we need to use in that FOC control, field oriented control, right? So we need to apply Clark and Park transformation. So Park transformation going to apply for current, right? So you have to apply Park transformation for that current, three phase current IA, IB, IC, and then you have to convert it into IDIQ. So this IDIQ should be aligned with already I told, right? So it should be aligned with the rotating magnetic field, and then we have to use two PA controller. So one PA controller used to for ID, and then another one is for IQ. But actually that ID reference, right? ID reference or ID control, right? Going to be set to 0, so that for minimizing the losses in the PMSM. And then IQ control going to be used to for control the torque of the PMSM, right? So we mostly apply the PA control in the IQ part, so to control the torque of the machine. So finally we are getting the two control quantity from the PA controller, that is called VD and VQ. Okay, next you have to convert that VD and VQ to VABC, and then the VABC, that means you can convert VD-VQ to VABC or VD-VQ to V alpha V beta, and then V alpha V beta will be processed via space vector modulation. Okay, so for generating the epithelium pulse according with vectors. Okay, so here you see that the control loop structure. So first you have to measure the stator current, then you have to apply Clark and Park transformation along with the rotor angle. So then we will get IDIQ, and then you have to provide ID reference, IQ reference input, and then you have to apply the PA controller, and then you have to generate VDVQ, and then you have to apply inverse Park transformation. So you have to generate V alpha V beta, and then you have to apply SVM, and then SVM space vector modulation will be generate the pulse. So that pulse will be used to control that inverter, and it going to be control the PMSM. So why we go with the SVM, right? So that SVM we are going to generate the pulse, right? Switching pulse based upon that output voltage. That means three phase output voltage into phase vector. We have to convert that output voltage of the inverter, right, into phase vector form. Now to choose that inverter. Okay, so that's that this technique is very efficient. Okay, when we have to convert that voltage into vector. Okay, and then and also you have to, this control concept, everything is based upon that alpha beta plane, and then it have combination of 6 active and 2 0 inverter states. And then here you see that, right, when you have to apply that phase vector modulation, then we need a 15% better DC bus voltage utilization, right, when compared to sinusoidal PWM. So that's why we go with that space vector modulation technique. And also you see that, right, when you apply that phase vector modulation, we can reduce the harmonic distortion to the output voltage. So when you reduce that distortion in the output voltage, right, then we can operate that motor very smoothly. Okay, and also it the heating problem also it going to be reducing the because of the SVM. And then most of the industry application, the system adapted with the field oriented along with the space vector modulation. And also in electric vehicle also and industrial automation also we apply that same kind of technique only. So that's why we go with that the FOC along with the PA plus space vector modulation. So next you have to see about that simulation of the system for that field oriented control of PMSM with the PA control and phase vector modulation. So this is the simulation model of that the current video. So it have DC source and then this is universal bridge. So this universal bridge going to be act as a three-phase inverter. So when you click this universal bridge, you will see that right. It have three bridge, okay, and then power trunk device is chosen as IGBT diode. So this will be is directly connected to the PMSM. So this is a PMSM, and then PMSM receive input. So this is the torque input, okay. So initial the step time will be we are fixing 0.05. Initial load torque will be 6 Newton meter and final load torque is 3 Newton meter. So here we are measuring the PMSM quantity. So here we are measuring the stator current IA, AB, IC, and then here we are measuring rotor speed omega r, and here we are measuring the rotor angle, okay, mechanical rotor angle theta m, okay. So first you have to measure the actual speed, right? So this actual speed, and then should be compared with the reference speed. So reference speed we are having. So here we are fixing initial radian per second is 100 and then final radian per second is 125 radian per second. When from time 0 to 0.5 the reference will be maintained at 100. After 0.05, right, it will be changed to 125 radian per second. So next you have to subtract both actual and reference and then it going to be processed via PI controller. So this PA controller will be generate the reference signal, okay. So reference signal, so reference signal nothing but IQ reference, okay. So this IQ reference, right, so this IQ reference going to be converted into ABC form. So here we are going to convert it into ABC form, okay. So in order to convert that this ID reference and IQ reference, so I already told, right, ID reference will be 0 to minimize the power loss in the PMSM. So this IQ reference will be act as a it going to be control the torque of the PMSM, okay. So just you have to combine this ID reference, IQ reference and then 0 current reference and then it will be converted into ABC and then input will be mechanical degree and then you have to convert it into electrical rotor angle, okay. So after converting this one, so you have to compare this IABC reference, right? So IAB reference with the actual IABC and then you have to convert this. After comparing that, we will get the error signal, right? So this error signal, right? Error signal will be act as a controlling signal. So that will be converted into alpha beta naught. Okay, so we are converting that single vector two plane quantity, right? Alpha beta. And then we are taking alpha beta and then it's going to be processed here phase vector modulation. So here we are using phase vector modulation and then we are having the input will be alpha beta component, okay. And finally we are getting the gating pulse. So here we have getting the gating pulse. So this gating pulse will be used to control this inverter, three-phase inverter of the PMSM. So this will be control that voltage and current, right, of the PMSM according with the reference speed and then IQ reference, okay. So then automatically the PMSM speed as well as torque going to be controlled in the system by means of this FOC control, right, field oriented control with the PA and space vector PWM, okay. Next you have to check the result. So here we are measuring the different quantities. So for here this scope will be used to measure the reference speed and actual speed and then this scope known as output voltage of the inverter and then current of the output current of the inverter and PMSM current and this is electromagnetic torque, right. So just I'm going to simulate this model. This is a reference 1000 radian per second. So initially system will be start to reach that reference around 0.02 seconds with overshoot, right. And the time of 0.05 second you will see that, right, it will be change the reference from 100 to 120, right? So then speed will be tracked that reference speed change command, right? And also it will be tracked couple of second, right? It will be track around 0.055 seconds. Okay, so here you see that this is the output voltage of that inverter for that input of the PMSM, and then here you see that this is the current for starting. So this is starting current and then the steady state current. So this is a current deviation due to change in the speed reference. So this is a current after stable operation. Okay. So here is this is the initial torque. So this is stable torque. Okay. And then this is a transient torque during that speed change in command. And then this is stable torque. Okay. So initial torque will be 6 Newton meter and then finally it will be 3 Newton meter. And also you'll see that variation of the current also. So here is that's the current at the time of 6 Newton meter. This is the current at the time of 3 Newton meter. Okay. So current will be reduced according with the load command change. And this is a switching pulse from that space vector modulation. Okay. So here you will see that, right, we control that PMSM speed effectively and the torque also controlled effectively. Okay, according with that FOC and PA controller and space vector modulation. So this is working of that field oriented control of PMSM with the PA controller and phase vector modulation. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you. Thank you so much. Bye bye.